Hello and welcome back to ENAE 788M, Hands-on Autonomous Aerial Robotics. In last lecture we talked about how the camera model works, and now we'll discuss about what are projective transform and how does the transformation affects your computer vision stuff. So have you ever used any computer graphics software like Blender, Autodesk Inventor, Maya 3D and stuff like that? So when you go to view, there are things like projective view or orthographic view. So things like that. So what do you mean by orthographic view? So when I draw a rectangle, a cube or a cuboid, my lines are still parallel. If you can see in orthographic, if I see in orthographic projection, this line and this line are parallel and they're actually equal, right? But if I take this image from a camera, which is not an orthographic view, which is a perspective view, or even as human, what we see is perspective view rather than orthographic view. So we'll get something like this. So these two cuboids are the same cuboids, but one is an orthographic view and the other one is perspective view. So the cuboid you are seeing on the left would look something like this. You see these lines which were actually parallel in orthographic view are not parallel anymore, and they need not be of the equal size. So your parallelism may not be preserved when you go from orthographic view to perspective view. But when we take images, or even as human, the images we are viewing are everything in perspective view. Okay, in orthographic views, parallel lines are parallel. This we discussed, right? So let's talk about this image. Like this is an image where you can see the road line, the railroad line, and you can see these two lines are actually parallel, right, in real world. But when you take an image, or if you see from this particular view, you'll be like, okay, these two lines are not parallel. If you see from the top view, maybe you'll like it might be parallel, like they might seem to be parallel. But if you see front to parallelly, these two lines are not parallel. Okay, so there's a concept in computer vision called vanishing points. So there's a vanishing point is a point which lies on the image plane, and what you do is you take two lines which are actually parallel in orthographic view and join them. Okay, the intersection of these two parallel lines in perspective view is called a vanishing point. Okay, but you can find multiple vanishing point in one image, and it may or may not lie inside the image. So you can see here this vanishing point lies inside the image, whereas this particular line which is drawn using these two parallel lines are lying outside the image. So it might or might not lie inside the image, right? So this will only this only exists in perspective view. If you are looking to find vanishing point in orthographic view, you won't find one, because the lines which are parallel in real world, which will actually be parallel in orthographic view. Okay, so how do we find these vanishing points? So the good part is, if you know the line L1 and L2, we can just take a cross product, right? So here the point P defined here can be written as L1 cross L2. Or if you want to find an equation of line using these points P1, P2, you will be like, okay, my line is equal to P1 cross P2. So as simple as that. Okay, so if you want to find this particular vanishing point, you'll be like, okay, I know the equation of line 1 and I know the equation of line 2, and like, okay, I'll just take out the cross product and I found a vanishing point. All right. So next is, you remember the projection equation from the camera model. So we have this scaling factor, the projected points equals whatever my intrinsic parameters, camera calibration K, and my rotation and translation, and the 3D world coordinates, right? So I open this up. I have the K, which has my focal length, my skew, my principal points, and for easiness, let's say my RNT is identity, right? And didn't translate. Rotation is identity and didn't translate. Okay. So for any given image I, which is a function of x comma y, I can say that my I goes under transformation T and I get some I dash, right? So what's going to happen is my x comma y is being transformed by some T, which is some 2D linear transformation matrix, and I'll get some x dash comma y dash, right? This is a 2D linear transformation. So this t can be in the form of a, b, c, d, and one of the part would transform the x-axis, the other part would transform the y-axis, right? So so my a, b, c, d, this entire transformation matrix is a combination of scale, rotation, shear, and mirror. So most general 2D linear transformation is a projective transform. Okay, let's learn more about what projective transform is. So let's figure out the different types of linear transformation first. So one of them is called isometry. Iso means same, metry means measure. So again, for any given image, I can write my for any given image, I can write my transformation matrix as epsilon cos theta minus sine theta, my translation in x, and similarly my sine and cosine term in translation y, 0, 0, 1. So this is isometric. So what it means is, if my epsilon is +1, that means my orientation is preserved. Like let's say I have a square, right? It remains the square of the same orientation. If my epsilon is -1, that means my orientation is reversing. So something like that. So let's assume this is sort of 45 degree, then my epsilon would be somewhere between -1 and 1. Okay. Then it has 3 degrees of freedom, 1 for rotation and 2 for translation. Okay, so theta is responsible for your rotation, and my tx and ty are responsible for my translation. Okay, special cases would be pure rotation, pure translation. Okay, so the important point to note here is my length, angle, and area are invariant. So if I have this transformation matrix, it won't change my length of the image or the pixels. It won't change my angle at the angle at which my pixels are distributed, or the area. Okay, so the next part is similarity, which is isometric plus scaling factor. Okay, so rather than epsilon in the previous case I have now s, and I don't have any constraint on s that it has to be +1 or -1 or something like that. So I don't have a constraint on s, so that's give you another degree of freedom, and that can vary from any value to any value, right? So s is responsible for the scale of the image. Now you can see that my 3 degree of freedom moved to 4 degree of freedom, so I have one scale extra as a degree of freedom. So again, this also preserve the shape but not the scale, so you will have the output something like this. So you had a square, and basically your image size increased and you get something like this. Okay, but again, this has invariance in terms of ratios of length, angle is preserved, ratio of areas, and the parallel lines are also preserved. Okay, the next most important transformation in 2D is affine transformation. So what it does is, rather than you having fixed theta for everything, you have a11, a12, a21, and a22, which can be totally independent of each other. And then you have 6 degree of freedom, 2 for rotation, 2 for translation, 2 for scale. Now 2 degree of freedom that you are getting from this is responsible for my scale ratio and orientation. Okay, so you'll get something like this. So let's say you had a rectangle. If you do an affine transformation, you might get a parallelogram, something like this. So your parallel lines would be invariant, ratio of parallel lengths, and the ratio of areas. Okay, now let's talk about what a proper projective transform is. So projective transformation is basically how you map a plane to another plane. So let's say you have an image like this, and you are projecting this image and basically transforming to different kinds of scene that you see here, right? So if I apply P1 transformation to this guy, I get something like this, right? And so on. You basically are trying to transform from one plane to another. That's what basically a projective transform means. So this comes from a thing called projective geometry. This is way before computer vision was there. So what projective geometry says is, you have an image, you take an image from a particular view, you take another image from a particular view. I mean, you take an image from a particular view and you take another image from a different view. So let's say you took an image when your camera center was at C1 and you took an image when your camera center was at C2. So these two camera center have a rotation and translation between them, or an RNT between them, and you're trying to take an image of the same planar surface. Now the image you will get would have some properties. For example, my parallel lines are projective in nature rather than orthographic that we discussed. So the parallel lines may intersect. Your circle may look like an ellipse. So if you have a circle on this ground, let's say something like this, right? Because assuming it's a planar surface and you are seeing at a certain angle, your image output might be something like an ellipse. When you convert the orthographic projection or orthographic view of a circle to a projective view, you may get an ellipse. You can prove that actually. Okay, read about it online. That's a very good proof. So next thing is the straight line nature is preserved. So any collinear points that you see in the image will remain collinear in your projective space. Okay. So this is a 2D comparison. Sorry, this is a comparison of 2D transformations. So we talked about Euclidean or isometric, which is 3 degree of freedom. We talked about similarity, which is 4 degree of freedom. We talked about affine, and there's another one which is full projective or perspective, also called homography. We'll discuss about that. So rather than having constraints, you have basically 9 elements. Okay. So in Euclidean, we said my length and area are preserved. In similarity, my angles and ratio of lengths are preserved. In affine, my collinearity and parallelism is preserved. And in full perspective or homography, my parallelism may not be preserved. The only thing I have is collinearity. Okay. So let's talk about homography. Okay, it's a special case. So we discussed how we could transform one image to other, right? We had this diagram when we are transforming one image to another. This is full projective. Let's say this surface is planar, right? Can I transform, or can I assume that this is a planar surface, and can I have a transformation between my C1 and the plane? So something like this. So this is also 2D, this is also 2D because it's a planar. Okay, capital X is the real world points, and small x is the points, projected points on the image plane. So what homography says is, I have a matrix H, which is a 3x3 matrix, such that my small x equals H times capital X. So this is how I'm transforming my world points to the image plane, right? So this is a plane to plane perspective transformation. So in homography, you need at least 2 set of points between these two, or 4 points basically, to solve for H. Okay, so let's say you have P1, P1 dash, P2, P2 dash, P3, P3 dash, and P4, P4 dash. This is a set of 4 points. Another thing is there's a confusion in the community that perspective transformation is different from homography, but it's not. That's because of computer vision. That's because of CV2. So when there are 2 functions basically, so if you're using the function called get perspective transform, you must provide a known good set of points. So that is the 2 sets of the 4 points must correspond to each other in the same order, and each point must be coplanar. Whereas the other function called find homography, that loosens this restriction a bit. So you can pass in 2 sets of more than 4 points, you suspect to be good, and it will use algorithm like ransack to find the best perspective transform between them. So basically they are trying to find the same thing, but because they have 2 different functions, depending on what their task is, the output of these 2 would be exactly the same. Okay, so let's say we have 4 points that we discussed. Okay, and you can compute the homography matrix H with your 8 points with a matrix system, such that the 4 correspondence points P1, P1 dash, and P2, P2 dash, and so on, can be written in a matrix form of 2 cross 9 matrix, as something like this. And if I basically write for all the four sets, I'll get this huge matrix, right? And this is my homography term, or all nine terms. Okay, and basically I can say that, okay, this is this big matrix, I'm calling it A, this I'm calling it H, and if my homography constraint holds true, I can also say that this matrix AH matrix must be equal to 0. Okay, so also we have an extra constraint saying that my norm of homography is 1. This is to avoid the obvious solution of H being all 0, right? So how do we solve it? SVT to the rescue. So for the matrix A, if I want to solve it, I can just write U sigma V transpose, and I'll be like, my solution of H is the singular vector of V. So this gives you a DLT, or also known as a direct linear transform homography, which basically minimizes the algebraic error. So this error is not geometrically meaningful, and so computed homography, this computed homography may not be as good as you expect. So one typically applies nonlinear least square with a better cost function, for example symmetric transfer error, to improve the homography. Okay, so this is more like linear, but they are nonlinear solution which will give you much better estimate for homography. Okay, so we discussed about how we can solve for homography or the transformation between two. Okay, so one more important thing here to notice, that once you have this H matrix and you already had this X comma Y, right, you can now project, given lambda, you can get the new projected X dash comma Y dash points. As simple as that. Okay, for derivation of how do we get this homography matrix and how do we project this, you can read this, you can click on this link and read it. The link will be in the description below in the YouTube link as well. So next point is, how do we find homography from R and T, or vice versa. So homography can be written as my rotation plus translation into normal of the plane formed by the collinear point set. Okay, so recovering R and T from my H matrix or vice versa is not that trivial. So if you want to learn about how to derive such equations, you can use this link. But people think it's trivial, but this is one of the things that there was a research paper, a deep study regarding something. How do you basically get your homography back from R and T? Okay, it's a sweet proof if you want to read. So why is homography important, right? We read about these stuff and how do we use it and how do we prove these things. But have you ever wondered that in your application, probably is a cam scanner, Google Photo Scan, or Adobe Scanner, you just take a photo and it tries to detect the corners, and it basically transform that image and make a very good looking PDF. The way it does it, it's basically looking for these four corners, and it assumes that, okay, this is planar, this is a paper, I can assume this is a good estimation for a rectangle. Once I have it, I applied that homography to my whatever resolution is, and basically I'm gonna stitch this point to this guy, this point to this guy, this corresponds to this guy, this corresponds to this guy, and I can compute the relative homography between these two. And once I do, I apply the homography matrix, and this transformation goes from this image to this image. Okay, and this is another cool thing called AMES Room, AMES Room. So the funny part is the height of this guy and this guy are exactly the same, but because of your projected transform and how this super amazing illusion works, it seems like this is as huge as Gandalf. This is probably a 10 feet guy and this is probably a 5 feet guy, right? But how it actually works is, it's a projected transform again. This is an illusion the way they make it, and if you see that these lines, these squares are not exactly equal. So the way they made it, this is a peephole, and your position of person A, it feels like this, but it's actually there. So they have basically gone through the reverse process of how your perspective transform would work. And now if you take this image, you'll be like, okay, it seems something different. So perspectives are very important. It is very important from where you are viewing, right? You can see in these two videos basically how just your viewpoint matters and how the images differ basically. So one more important thing I would like to add is, you remember we talked about in controls how the position control of a quad rotor works, right? So one thing that quad rotor inertial measurement unit are not good at is how to basically find the pose or the position and the orientation of the quad rotor to do a position hold. So what people do is they use homography for this. So let's say you have a quad rotor flying, right? You have a down facing camera, and you can, it's fair to assume that my ground or my ground floor is plane basically, right? It's a planar structure. Most likely than not, it would be a plane. So using that assumption, my homography estimation, I can say, okay, my quad rotor was here, in the next frame the quad rotor is here, and because I can compute homography between these two guys, I can actually estimate how much I moved. But the catch here is it's not to scale. So it might be, okay, it might say, okay, I moved 1 unit from here to here, but I don't know if that 1 unit is 1 centimeter or 1 millimeter or 1 meter, right? So to remove the ambiguity of scale, people what do is they either used the scale information from inertial measurement unit, or they use scale information from the down facing LiDAR or down facing sonar or whatever the distance sensor is. So that's one cool thing about perspectives and homography that people use. So that's it for this class. We'll talk about the problem of structure for motion in the next class. So see you then. Bye.